Leon Henkin (1921–2006) was an American logician renowned for his significant contributions to mathematical logic, particularly in the development of model theory and type theory. He is best known for his Henkin's completeness proof, a seminal work that provided a new proof of the semantic completeness of first-order logic and extended completeness results to higher-order logics, introducing innovative techniques like Henkin constants and general models, also known as Henkin models. These contributions revolutionized the understanding of formal systems by demonstrating that every consistent set of sentences has a model. Henkin also made notable advancements in algebraic logic, co-authoring the influential work Cylindric Algebras with Alfred Tarski and J. Donald Monk. While primarily a logician, Henkin's work intersected with linguistics through his exploration of logical languages, including the development of Henkin quantifiers, which broadened the study of partially ordered quantifier structures in formal and natural language semantics. His intellectual legacy, combined with his efforts in mathematics education and advocacy for diversity, solidified his impact as a scholar and educator at the University of California, Berkeley. Leon Henkin was born in Brooklyn, New York, on April 19, 1921. He grew up in a close-knit family, living with his cousins during his childhood. He attended New York City public schools, including Lincoln High School, and graduated at age 16 to attend Columbia University. He earned a BA in mathematics and philosophy from Columbia University in 1941. In 1941, he was admitted to the graduate program at Princeton University, where he received an MA in mathematics in 1942. During World War II, from 1942 to 1946, he served the U.S. war effort, working on the Manhattan Project and eventually becoming the head of the Separation Performance Group at Oak Ridge. He returned to Princeton in 1946 to complete his Ph.D., which he earned in 1947 under the supervision of Alonzo Church. His dissertation contained his now famous proof of the completeness of first-order logic. Henkin, L. 1949. The Completeness of the First-Order Functional Calculus. The Journal of Symbolic Logic, 14-3, 159–166. This foundational paper is one of Henkin's most famous contributions. It introduced a new proof of the completeness theorem for first-order logic. Unlike Gödel's original proof, which was non-constructive, Henkin's proof was more direct and introduced the concept of a Henkin-style model construction. This method, which involves adding new constant symbols to a language to ensure the existence of a model, became a standard technique in model theory and is a cornerstone of modern logic. Henkin, L. 1950. Completeness in the Theory of Types. The Journal of Symbolic Logic, 15-2, 81–91. Following his work on first-order logic, Henkin extended his completeness proof to the theory of types, also known as higher-order logic. This paper demonstrated that for a specific class of higher-order systems, those based on Henkin semantics, a completeness theorem could be established, a result that was not possible for the standard or full semantics of these systems. This distinction between types of semantics remains a crucial topic in the study of higher-order logic. Henkin, L. 1953. Banishing the Rule of Substitution for Functional Variables. The Journal of Symbolic Logic, 18-3, 201–208. In this paper, Henkin addressed a technical but important issue in higher-order logic concerning the rule of substitution. He showed how to reformulate a system of higher-order logic to eliminate the need for an explicit rule of substitution for functional variables. This simplification made the logical systems more elegant and easier to work with, helping to clarify the relationship between variables and the objects they represent. Henkin, L. 1953. Some interconnections between modern algebra and mathematical logic. Transactions of the American Mathematical Society, 74, 410 to 427. This work explores the deep connections between algebraic structures and mathematical logic. Henkin demonstrated how certain logical systems could be represented by algebraic structures, particularly through his work on cylindric algebras. This paper helped bridge the gap between two seemingly distinct areas of mathematics, showing that tools and concepts from one could be used to solve problems in the other. Henkin, L. 1953. Some Notes on Nominalism, The Journal of Symbolic Logic, 18-1, 19-29. This paper delves into the philosophical foundations of mathematics, specifically addressing nominalism. Nominalism is the view that abstract objects like numbers and sets do not exist independently and that mathematical statements are statements about language or symbols. Henkin explored the logical and philosophical implications of this view, contributing to the ongoing debate about the nature of mathematical reality. Henkin, L. 1954. A generalization of the concept of omega consistency. The Journal of Symbolic Logic. 19-3, 183-196. This paper generalizes the concept of omega consistency, a property of formal systems introduced by Kurt Gödel. Henkin's generalization was a significant step in the study of model theory and the limitations of formal systems, expanding on the ideas related to Gödel's incompleteness theorems. It showed that the ideas of consistency and completeness could be extended in interesting and useful ways beyond the original formulation. Henkin, L. 1955. The Nominalistic Interpretation of Mathematical Language. Bulletin of the Belgian Mathematical Society. 7, 137-141. Continuing his exploration of nominalism, Henkin provided a clear and concise summary of the nominalistic perspective on mathematical language. This paper outlined how a nominalist might interpret mathematical statements without committing to the existence of abstract objects, offering a philosophical framework for understanding the role of language in mathematics. Henkin, L. 1955. The Representation Theorem for Cylindrical Algebras. In Skolem, T. H. Hassenjaeger, G. Kreisel, G. Robinson, A. eds. Mathematical Interpretation of Formal Systems, pages 85-97. In this paper, Henkin presents a representation theorem for cylindric algebras, a class of algebraic structures designed to model first-order logic. This work, developed in collaboration with Alfred Tarski, is a cornerstone of algebraic logic. It shows that any cylindric algebra can be represented as an algebra of sets of sequences, providing a powerful tool for studying logical systems from an algebraic perspective. Henkin, L. 1957. A generalization of the concept of omega completeness. The Journal of Symbolic Logic. 22-1, 1-14. Building on his earlier work, Henkin extended the concept of omega completeness to systems with arbitrary sets of constants. This paper further generalized the metalogical properties of formal systems and explored the conditions under which a theory can be considered complete in a broader sense. This was an important contribution to the development of model theory. Henkin, L. 1960. On Mathematical Induction. The American Mathematical Monthly. 67-4, 323-338. This paper provides a detailed and insightful examination of the principle of mathematical induction. Henkin explored the different forms of induction and their logical foundations. He clarified its role as a fundamental proof technique in mathematics and discussed its various applications and limitations, making it accessible to a wider audience. Henkin, L. 1961. Mathematical Induction. In Ma Film Manual No. 1, The Mathematical Association of America, University of Buffalo, Nueva York. In this piece, which accompanied an educational film, Henkin provided a pedagogical treatment of mathematical induction. He presented the concept in a clear and instructional manner, focusing on its practical application in problem solving. This work highlights his commitment to improving mathematics education and making complex ideas understandable. Henkin, L. Tarski, A. 1961. Cylindric Algebras. In Dilworth, R.P. ed. Lattice Theory. Proceedings of Symposia in Pure Mathematics. American Mathematical Society, 2, 83-113. This collaborative paper with Alfred Tarski is a foundational text in the theory of cylindric algebras. It systematically lays out the properties and structure of these algebras, which provide a powerful algebraic framework for studying first-order logic. This work established the field of algebraic logic as a significant area of research. Henkin, L. Smith, W. N. Verino, V. J. Walsh, M. J. 1962. Retracing Elementary Mathematics. Macmillan, New York. This book, co-authored by Henkin and his colleagues, was an educational text designed to provide a rigorous and modern look at elementary mathematics. It aimed to help teachers and students understand the logical and foundational principles behind basic arithmetic and algebra, reflecting Henkin's long-standing interest in improving mathematics pedagogy. Henkin, L. 1962. Are Logic and Mathematics Identical Science, Volume 138, 788-794. In this thought-provoking article, Henkin addresses the philosophical question of whether logic and mathematics are the same thing. He explores the different arguments for and against this view, discussing the relationship between formal systems, truth, and the nature of mathematical knowledge. He presented a nuanced perspective on this classic philosophical problem. Henkin, L. 1963. New Directions in Secondary School Mathematics. In Ritchie, R.W. ed. New Directions in Mathematics, 1-6. Prentice Hall, New York. This article reflects Henkin's direct involvement in mathematics education reform. He discussed the need for new approaches to teaching secondary school mathematics, advocating for a greater emphasis on conceptual understanding, logical reasoning, and the fundamental principles of the subject rather than rote memorization. Henkin, L. 1963. An extension of the Craig-Linden interpolation theorem. The Journal of Symbolic Logic. 28-3, 201-216. This paper presents a significant extension of the Craig-Linden interpolation theorem, a key result in mathematical logic. The interpolation theorem guarantees that if one sentence implies another, there is a bridge or interpolant sentence that uses only the common symbols of the two sentences. Henkin's work provided a more general version of this theorem, deepening the understanding of logical properties and their relationship to language. Henkin, L. 1963. A Theory of Propositional Types. Fundamenta Mathematici. 52, 323-344. In this paper, Henkin developed a theory of propositional types, a formal system that combines elements of propositional logic with the theory of types. This work explored the expressive power of different logical systems and the ways in which they can be used to model mathematical concepts, pushing the boundaries of logical theory. Henkin, L. 1971. Mathematical Foundations for Mathematics. The American Mathematical Monthly. 78.5, 463 to 487. In this influential article, Henkin provided a broad overview of the mathematical foundations of mathematics. He discussed the role of logic, set theory, and model theory in establishing a rigorous basis for mathematical knowledge. The paper serves as an excellent introduction to these topics, summarizing their historical development and their significance. Henkin, L. 1975. Identity as a Logical Primitive. Philosophia 5, 31-45. This paper addresses the role of identity in logic and philosophy. Henkin explored whether identity should be treated as a fundamental, or primitive, concept within a logical system, or if it can be defined using other concepts. This work contributed to the philosophical debates surrounding the nature of identity and its place in formal systems. Henkin, L. 1977. The Logic of Equality. The American Mathematical Monthly. 84.8, 597-612. Expanding on his work on identity, Henkin provided a comprehensive overview of the logic of equality. He discussed the axioms and rules governing the use of the equality symbol equals in formal systems, showing how equality functions as a cornerstone of mathematical reasoning and demonstrating its central importance in various logical theories. Henkin, L. 1995. The Roles of Action and of Thought in Mathematics Education. One Mathematician's Passage. Fisher, N. D. Keynes, H. B. Vogrich, Ph.D. eds. Changing the Culture, Mathematics Education in the Research Community, CBMS Issues in Mathematics Education, Volume 5, pages 3-16. American Mathematical Society in cooperation with Mathematical Association of America, Providence. In this autobiographical and reflective piece, Henkin shared his perspective on the interplay between action and thought in mathematics education. He recounted his journey as a mathematician and educator, arguing for the importance of active learning and hands-on problem solving to complement theoretical understanding. Henkin, L. 1996. The Discovery of My Completeness Proofs, Bulletin of Symbolic Logic, Volume 2 127-158. In this final paper, Henkin offered a historical and personal account of his famous completeness proofs. He described the intellectual process, the challenges he faced, and the key insights that led to his revolutionary method. Leon Henkin died on November 1, 2006, at the age of 85, in Oakland, California.